If there's one thing that you take away from this course, it should be that data structures have rather uncreative names. Trees are data structures that, well, look like trees. A tree starts from a place called a root, and you add data to it called branches. A big tree will fan out with lots of different branches in lots of different directions, just like a real tree. There are plenty of other tree terms related to these data structures. They have leaves, a collection of trees is called a forest, etc. Try to keep a straight face as we dive in and see what trees are all about. Trees have a lot of properties that make them useful. However, a tree is really just an extension of a linked list. A linked list has one element at the front and a next pointer to another element, and so on. A tree is similar. The first element is called the root. Instead of having just one next element, a tree can have several. A linked list is often drawn horizontally, but a tree is normally drawn vertically like this. Just like a linked list, each element on a tree contains some data. The individual elements in a tree that contain values are often called nodes. Let's add a few more constraints on what we call a tree. First of all, a tree must be completely connected. That means if you're starting from the root, there must be some way to reach every node in the tree. Here is an example of unconnected nodes. So this definitely isn't a tree. Next, there must not be any cycles in the tree. A cycle occurs when there's a way for you to encounter the same node twice. For example, in this tree, there's a connection back to the root. If I start at the root, then I'll get back to the root. The same goes for this tree. If you ignore the arrows, you can still go in a circle. This counts as a cycle, so beware. Okay, I'm going to throw some terms at you. Get ready. You can describe a tree in terms of levels, or how many connections it takes to reach the root plus 1. The root is level 1, and nodes directly connected to it are on level 2. Nodes in a tree are often described as having a parent-child relationship. In this system, a node at a lower level is a parent, and the node connected to it at a higher level is a child. A node in the middle can be both a parent and a child. It depends what it's being compared to. Keep in mind that this isn't a real family tree, where children all have two parents. Here, children are only allowed to have one parent. If a parent has multiple children, those children are considered siblings of each other. You can talk about ancestry in a similar way. A node at a lower level can be called an ancestor of a node at a higher level, which is the descendant. The nodes at the end that don't have any children are called leaves, or external nodes. A parent node is called an internal node. You can call connections edges and a group of connections taken together as a path. The height of a node is the number of edges between it and the furthest leaf on the tree. A leaf has a height of 0, but the parent of a leaf has a height of 1. The height of a tree overall is just the height of the root node. On the flip side, the depth of a node is the number of edges to the root. Height and depth should move inversely. If a node is closer to a leaf, then it's further from the root. Phew, glad that's over with. Time to learn some more about trees. When we looked at list data structures, traversal was pretty straightforward. We just needed to go through the list, in order, to make sure we looked at every element. Trees aren't linear, so there's no clear way to traverse through everything. Suppose we start at the root. Do we go left first or right first? Should we completely traverse one subtree or one section of the tree, including a parent and all of its descendants? Or traverse everything at the same level first? Traversal in a tree is a bit more complicated, but it's equally important. We can't search or sort elements unless we have a way to make sure we can visit all elements first. There are two different broad approaches to tree traversal. One is called depth-first search, or DFS for short. In DFS, the philosophy is, if there are children nodes to explore, exploring them is definitely the priority. We'll take a more in-depth look at what that means in a minute. The alternative is called breadth-first search, or BFS. In BFS, the priority is visiting every node on the same level we're currently on before visiting child nodes. BFS and DFS are kind of vaguely defined, since we can apply their principles but actually traverse the tree in several different ways. For trees, a level order traversal is a BFS with a more exact algorithm to implement. A level order traversal is exactly what it sounds like. Start at the root, then visit its children on the second level, then all of their children on the third level, until you visited every single leaf. By convention, we start on the leftmost side of the level and move right. This traversal is definitely a BFS. We're visiting all nodes at the same level before moving on to child nodes. There are several different approaches to DFS in trees. First, we'll talk about pre-order traversals. To me, the pre says, check off a node as soon as you see it before you traverse any further in the tree. There are other methods of traversal in which you check off nodes after you've seen their children, so this rule is really important to keep in mind. We start at the root and immediately check off that we've seen it. Next, we pick one of the children, normally the left one by convention, and check it off too. We would continue traversing down the leftmost nodes until we hit a leaf. We check off the leaf, and from there go back up to the parent. Now we can traverse to the right child and check it off too. We're done with this subtree, so we can travel back up to the root and look at its right child. We do the same steps until we've seen everything. Cool, we're done. This might seem intuitive, but it'll make more sense once we compare it against a different type of traversal, like an in-order traversal. The trick here is that we're moving through the nodes in the same order since this is still a DFS and we need to explore all children first. However, this time we're going to check off the nodes in a different order. We're only going to check off a node when we've seen its left child and come back to it. Alright, let's see what this looks like. Again, we start at the root. Since we haven't seen the left child yet, we have to keep traversing down until we hit a leaf. We check off the leaf and move up to the parent. Because we've seen the left child now, we can actually check off the parent this time. We move on to this right node, which has no children, so we can check it off too. We go back up to the root and repeat all of this on the right side until we're done. Why is this called in order? Well, we pretty much went through the nodes in order from the leftmost to the right. We had to move up and down a lot, but if you just look strictly at left to right, we actually did go through everything in order. Lastly, we have the post-order traversal. This time, we won't be able to check off a node until we've seen all of its descendants, or we visited both of its children and returned. Similar steps. We begin at the root, don't check it off, but continue down to a leaf. We check off the leaf and move to the parent. This time, we don't check off the parent though, we just move on to the right node. Once we've checked off the right child, we can go back up to the parent and finally check it off too. Again, we'll skip over the root node and just move all the way down to the right. Once everything there is good, we can move back up to the root and get it. Binary trees are simply trees where parents have, at most, 2 children. This means nodes can have 0, 1, or 2 children. Those children might even be null, but that's okay. Let's see what search looks like in a binary tree. We could start off by using any of the traversal algorithms to go through the tree. Because there's no real order to the elements, I need to go through every single element in the tree if the value I'm looking for doesn't exist. There are no cool tricks here, so we're stuck with a linear time search. A delete operation often starts out with a search since you need to find the node you want to delete. If you're deleting a leaf, you can simply delete it and move on. However, if you delete an internal node, you'll suddenly have a gap in the tree. If the node you deleted only has 1 child, you can actually just take it out, move the child up, and attach it to the old node's parent. If you're trying to get rid of a node that has 2 children, you have a few options. You could promote the child up, just like you did before. Of course, it can't always be that easy. What if both children also have 2 children? In the worst case, you'll need to keep traversing down the subtree until you hit a leaf. Since there's no real order requirement here, you can just put the leaf where your deleted node was without a problem. Since there's a search involved and some additional work to shift around the elements after a deletion, the runtime is linear. Inserting an element into our tree when it has no order is relatively easy. We'll just tack our node onto another node. Maybe it's a leaf, or maybe it's a parent with only 1 child. We only need to make sure that we're obeying the 2 children rule. We're given the root at the beginning, and we'll need to keep moving down the tree until we find an open spot. How long will it take to find an open spot? The worst case is that we travel down the longest path until we find the farthest leaf. In that case, we'll travel through the number of nodes equal to the height of the tree. But what is the height of a binary tree? Like we did with our sorting algorithms, let's look at some examples and reason through it. Here are two different trees. We can call these perfect trees since every node except the leaves on the last level has 2 children. It looks like this tree with 3 nodes has 2 levels, and this one has 7 nodes and 1, 2, 3 levels. As the tree grows bigger, each new level has the capacity to hold a number of nodes equivalent to a power of 2. Mull over that for a second. Each node can have 2 children, so each new level can have twice as many nodes as the one before it. Since we've gone back to talking about powers of 2, your mind should jump to log n. Does that apply here? Let's take a look. The number of levels increases near a power of 2. And now we have a good visualization to understand why. At every level, we're adding roughly twice as many elements. Every time we need to add a new level, or in a binary search, divide our array another time, it's because we're giving ourselves the space to allow for about twice as many elements. Remember that we're adding a power of 2 at each level, so when we count up the nodes overall, it won't be exactly a power of 2. Having 3 levels doesn't mean an overall node count of 8, but it does mean that the 4th level itself will have 8 elements in it. Trees inherently aren't really organized. When we use a tree, we know what the overall structure looks like, but we don't know where a specific element will be. It turns out that we can add some rules about the ordering of elements to our trees to accomplish certain tasks really fast. In the coming videos, we'll talk about some common tree types with specific rules regarding the ordering of elements. As we go, don't let yourself get so caught up in understanding the types of trees that you forget the big picture. When would you want to use these structures? What tasks would they speed up? What are the pros and cons of each approach? There's a more specific type of binary tree called a binary search tree. A binary search tree, or BST, is definitely a binary tree. That is, every parent node has at most 2 children. But just as an array is a type of list, a BST is just a type of binary tree. There's a specific rule for how the values associated with each node are arranged. BSTs are sorted, so every value on the left of a particular node is smaller than it, and every value on the right of a particular node is larger than it. Because BSTs have this structure, we can do operations like search, insert, and delete pretty quickly. Let's say we want to find 7. We would start at the root. We see 7 is greater than 5, so we go right next. Since our next element is 8, we know our next move is left. And in just a few steps, we found it. You may have noticed that we didn't need to search every element to figure out where the one I was looking for belonged. We just had to look at one value in each level of the tree, and then we could make a decision with just a comparison to my element. That means the runtime of a search on a BST is just the height of the tree, which we proved was log n when we learned about inserting. Inserting in a binary tree is pretty much the same process. You start at the top, and you can make quick decisions about where to look at each step by comparing to the element you want. Binary search trees are nice to look at when they're full, but there's no rule that states that BSTs need to look that way. This is a completely legitimate BST, but it looks very different. There are 2 or fewer children for every parent, and everything on the right is bigger than its parent. We call this an unbalanced binary tree, since the distribution of nodes is skewed to the right side. A weird structure like this could start at the root, but it could also take place in one of the subtrees. You can also consider this to be the worst case scenario for a BST. When the tree looks like this, search, insert, and delete all actually take linear time in the worst case. Here, the worst case would be searching through every element from the root to the leaf. Thus, the average case for these operations is big O of log n, and the worst case for all of them is big O of n.
Now we're going to learn how to work with trees in code. Now, a common question you may ask whenever you're learning anything is, will I ever use this in real life? And I'd say especially with tree data structures, the answer is yes. Trees show up quite a lot in software engineering, in databases, anytime you're dealing with storing data. And the nice thing about trees is you're able to retrieve values you need more quickly because you don't actually have to touch upon all the nodes stored in the tree before you find what you're looking for. Also, when you're studying machine learning, trees show up again in tree-based machine learning models, such as variants of decision trees. So here are the coding practice objectives for this lesson. You'll learn how to create a binary tree in code from scratch. You'll learn how to traverse a tree, depth first search and breadth first search in code. And you'll also learn how to create a binary search tree, and also how to insert, search, and delete nodes. And just keep in mind, the average time complexity for these tree operations is log n. A good way to remember that is when you think of trees, think of logs. Okay, so now we're going to learn how to code up a binary tree from scratch. So first, you'll want to build a node class, and I would recommend, if you haven't done this in a while, then first draw out on a piece of paper how a tree looks like, something like this, and then think about what are the attributes that a particular node needs to store. And the hint is there's going to be 3 things. So the instructions are define a class node, and define a constructor that takes no arguments and sets the 3 instance variables to none. Okay, so go ahead and try it out, and then check out the solution. Okay, so now let's see how we would code up the node class. First, in some pseudocode, you can think there's a node class, and there are 3 things that I need in there. There's the value that it's storing, and also there's pointers to the left child and the right child. So that means there's a value, there's the left child, and then there's the right child. Okay. So now let's define this with better syntax. So it's going to be a class node. It's going to inherit from object. And it mentions define a constructor. So here's the constructor. Okay, and it doesn't take any arguments, so just self. And so it's going to set these 3 values to none. And remember, these are instance variables, so I'm saying self.value, self.left. Okay, so there you go. We have a node. And let's see if it works. Okay, so I checked that it's got these 3 values. Looks like it's doing okay. Okay, so next we'll just want to modify the constructor so that it takes a value as a parameter. So you can copy what you just made and modify the constructor so it takes an optional value, which assigns it to the node's value. Otherwise, it will set the node's value to none. Go ahead and try this out. Okay, so now let's go ahead and reuse the code we already generated and then modify the constructor so that it takes in a value. So now it takes in a value, but also in case it doesn't, we just want to give a default value of none. And then we want to set that value to our node's value here. Okay, so let's check if this works. We'll create a node with no value entered, and it should work. Also, we'll create a node that takes in a value, and that should also work. Okay, as you can see, this node prints out. This node also prints out with a stored value apple. Alright, so now building on what you've already built, you can copy what you've already built earlier. Add functions to set and get the value of the node. In other words, add functions called getValue and setValue to the node class. Okay, so now let's go add setters and getters. Let's first go ahead and just reuse what we already did. And we want a getValue. I'll fill this in soon. And we also want a setValue. And so notice here we want to set it to something, so it's going to also need to take in a value. So to get value, we can return self.value, and to set the value, we can say self.value is equal to value. Alright, next let's add some setters and getters for assigning left and right childs. So define a function setLeftChild and a function setRightChild. Each function takes in a node that it assigns as the left or right child, respectively. Note that we can assume that this will replace any existing node if it's already assigned as a left or right child. So also define the getLeft and getRightChild functions. And one note for you is, you may be wondering why you're starting from a blank cell every time. I think for coding interviews it's good practice because you'll usually not be given any scaffolding code. You'll just be starting from even a blank sheet of paper, not even a computer. So I do encourage you to try this out, but don't worry, I'll be coding the solutions along with you. Okay, so now let's add the getter and setters for the children, we'll go ahead and use what we've already created for the node. And we want to define set left child, and I'll fix these later, just setting it up, set right child, get left child, and get right child. Okay, so now we have these functions defined, and let's go ahead and fix these. So we want to set the left child. It's going to be taking in some node that it will set it to, and it's going to set the left self.left equal to that node that's passed in. Similarly, for set right child, it's going to take in some node, and then it's going to set the right node pointer to that node. Now to get the left child, we can just return self.left. Similarly, for the right child, we're going to return self.right. Okay, awesome. Let's check if it works. So here we can check by creating 3 nodes. There's going to be node 0, node 1, and node 2. They each store a value, apple, banana, and orange. Now for node 0, I will set its left child to node 1, which is banana, and node 0's right child I will set to node 2, which is orange. We'll just print it out to see if it works, and indeed, node 0's left child is banana, and node 0's right child is orange. Okay, so your next task is to check if the left or right child already exists. In other words, if it's already been set to some node and it's not just none. So define a has left child and a has right child so that they return true if the node has a left child or a right child, respectively. You can go ahead and reuse the code you created earlier and just add these 2 functions. Okay, so now let's go ahead and define has left child and has right child. We'll just use the code we already generated earlier, and we'll just add on has left child and has right child. Okay, so let's think about it. When you look at a tree node, let's go back to the visual at the very top. So apple, it has a left child and it has a right child. Banana has a left child set to dates, and its right child, it would be set to none, meaning it doesn't have anything, doesn't have a right child. Okay, so it could either be none or not none. So that's how we tell whether it has a child or not. Going back to task 5, this means that if the left pointer is not none, then that means it's something, it's some node, some non-null value. So that means that it has a left child, return true. Otherwise, that means that the left pointer here is actually set to none, so we're going to return false. Okay. All right, so notice that this is fine, but it's slightly inefficient. And when you get into coding interviews, you'll be asked sometimes, instead of writing an if-else block, how can you write it all in one line? And so what you'll notice here is that, what is this conditional doing? Self.left does not equal none. That's actually returning a Boolean value. This is going to evaluate to either a true or a false. And in this case, when it is true, it goes down to here, and then what does it do? It returns true, because this function has left child is also trying to return a Boolean, either true or false. So similarly, when this expression evaluates to false, then we jump to the else block, and then what is the action we take? We're returning false. Okay. So notice what we could actually do here is we can skip this step, make it a little bit more efficient, and then just say return whether self.left is not equal to none. So there you go. We can do the same here for checking if it has a right child. If the right child's pointer is not none, that means it has a right child. Okay. Otherwise, it doesn't, and it would return false. Okay, so let's just check this out. We have 3 nodes that we'll create, and then we'll also check if node 0 has a left child or a right child. So at this point, these are all separate nodes, and nothing has been added as a child to another. And then here, we're going to add node 1 as the left child and node 2 as the right child. Okay, so it's going to be, there's an apple, and then on the left there's banana, and on the right there's an orange. Okay, and then we'll check again using these functions that we just defined. Does it have a left child? Does it have a right child? So you can see beforehand, before we add the children, the answer is false. And then after we add the children, the answer is true. So it works. Now our next task is to create a tree class. So create a class called tree that has a root instance variable of type node. Also define a getRoot method that returns the root node. So visually what I mean is this. A tree is a collection of nodes. We've already been defining the node class. And the tree will just need to point to one node, which is the one at the very top, because from there, the root node, we can access all the other nodes. So here, just create a new class. We're not copying over the node class anymore. Create the tree class, and then you can check your solution in the next video. Okay, so now we're going to define the tree class. So you can start with pseudocode and just think that a tree contains a root node, and we'll also have a function that's going to get that root node. But now let's write it in Python. So we have a class tree, inherits from object, and let's define the constructor, and then it's going to set the root node is equal to none, okay? And then let's define the getRoot method. It's going to return the root. All right, there you go. So now let's modify the tree constructor so that it takes an input that initializes the root node. So you can choose between two options when you think about it. The constructor can either take a node object, or the constructor takes a value and then creates a new node that stores that value. Okay. So you can think about it, try both possibly, and then we can go over the solution and discuss which one might be better. Okay, so let's try doing things both ways and discuss what we might think is better. Okay, so first, I'll just take what we already have, and here the first option is the constructor can take a node itself and then set the root to that node. Okay. And another option, option 2, it can take something that we assume is a value, and then it'll create a new node based on that value, and then set that to the root node. Okay. So when you think about an end user using your tree class to store their data, you could imagine that they probably don't really want to worry about what's internally inside your tree class and just be able to use it to put their data in there. So in that case, it probably would make more sense to have the values that the functions take in, the parameters, be the values that the user wants to store, instead of assuming that they know how to create a new node class and then work with that. So I'd recommend writing it this way. Now we're going to look at tree traversal. So traversing a tree means we're walking through it in some way so that we're visiting all the nodes once. So traversing is used for searching for a value, inserting a value, or deleting a value from the tree. And there are two types, depth first search and breadth first search. And for depth first search, there's three subtypes: pre-order, in-order, and post-order. We're going to look at pre-order traversal in detail. So in pre-order traversal, we start at the root, we visit it, then we check if there's a left child. If so, we go down to the left child. So now we're in B, we visit it, and then we check if there's a left child. If so, we'll visit it. So now we're going to visit D. So now we're in D, we visited D, and now we're going to check if there's a left child. Nope. So then we'll check if there's a right child. Nope. So then we'll go back up, check if there's a right child. In this case, nope. Go back to A, check if there's a right child. Yes. So now let's go here, and now we visit C. Again, check if there's a left child. Nope. So then we go to right child. No. And then we visited all the nodes. Okay, so now we're going to walk through some code in the notebook that's going to generate a sample tree that we can practice traversing. So it's going to look like this. It's going to have apple at the root, and then also banana, cherry, and dates. And we're using a node class, which we wrote the code for this in the previous exercise. All I'm doing is adding these functions, overriding them rather, so that when I call print on them, I can see the value inside the node. And then these lines of code are just adding these nodes as children within this tree where the root node is apple. Okay, so now we're going to look at this with more detail, because what's going on is we're actually going to use a stack to help us track what nodes we visited. Again, we're starting at the root node, so we visit it, we check if it has a left child, and because it does, we add B to the stack, and now we're here, and also we visit B. So now we check if B has a left child, and it does. So we add D to the stack. And once we get to D, we also visit it. And then we check if it has a left child. Nope. Right child. Nope. So now what happens is we're done with D. We're actually going to pop it off the stack. So you can see D is going to disappear now from the stack. Now we're at B. We check if it has a right child. Nope. So actually we're done with B. And we're going to pop B off the stack. Okay. And now we're back at A, the root node. We're going to check if it has a right child. And it does. So now we're going to add C to the stack. And when we get to C, we're going to visit it. So now the visit order is A, B, D, and then C. Now we check for C's left child, nope. Right child, nope. That means we're done with node C, and we can pop it off the stack. Now we're at A. We've already visited A's left subtree and right subtree, so we pop it off the stack as well. Great. So now we visited all the nodes. Now we're going to try to translate our algorithm from our visual into writing code. And I recommend trying to write a little bit at a time without a for loop yet. And this will help you see what you're doing bit by bit. So we're going to create a list called visit order, and we're going to create a stack that's going to help us keep track and walk back our path. We'll start with the root node, which is Apple, right here. We're going to grab it and push it onto the stack. So as you can see, now we have Apple on the stack. We take what's on the top of the stack and we're going to visit it. So we're appending it to the visit order list. So now you can see that the visit order now contains Apple. The stack contains Apple. Okay, so now what do we do with the node at the top of the stack? We're going to check if it has a left child. So we write an if statement. If it has a left child, then what do? We want to get that left child, and we want to push it onto the stack. So now we can see the left child that we found was banana. We push it on the stack on top of apple. And now the next step is, what's on the top of the stack? Banana. So we're going to visit it. And to say we visited it, we're just appending it to this visit order list. And you can see now that when we visit node banana, now we see that we visited banana after apple. And then again, we check the top of the stack is now banana. And so does it have a left child? It does. And so we're going to grab it and push it onto the stack. So now you can see that we're repeating a pattern. So this is where we would eventually want to use a for loop. But this is kind of a good way to get started. So I walk through the entire tree traversal here, but if you feel like you get the idea and you want to go skip ahead to the function itself, then just skip ahead to here, pre-order traversal using a stack. Pre-order traversal using the stack. Here's an implementation of doing pre-order on a tree, but there's something missing which is causing an infinite loop. So let's see what we can learn from this. So this pre-order with stack buggy is taking in a tree. It's also going to keep track of the visits with this list, and it will also use a stack to help it backtrack. It starts out getting the root and pushes it onto the stack. It also makes sure to take the top of the stack. So this is for clarity purposes, but technically this node was already set to the top of the stack because it just pushed that node. But here you can see we're going to visit the root node before continuing. So we do that by appending it to the visit order list. And I added some counter and a limit to the count just so that this while loop will stop after a while. And then we can look at the output and see what's happening. Okay, so you can see that it's going to check if the node has a left child. Otherwise, it will also check if it has a right child. Otherwise, it will check when it's either visited the left and right children or there's a leaf node, then it will start to backtrack, go back up the tree, which means it would pop the stack. So let's take a look more closely here. When we're checking if there's a left child, then we'll go down and traverse into that left child, meaning we'll also keep track of it by pushing it onto the stack. And then when we look at the top of the stack, we're going to go into that node. And when we go into that node, because it's pre-order traversal, we're going to visit that node. And to denote that, we're appending it to the visit order list. And for the right child node, it's the same thing. When we get to a leaf node, for instance, we would pop that leaf node off the stack, and if the stack still has something in it, then we'll move on to that top of the stack. So it's sort of as if you were looking at a child node and then popping it off the stack so that you're moving up to the parent node. And there's also the case where when we've finished going through all of the nodes in the tree and we're back up to the root node, then that happens here where the stack is empty. Then we'll set the node to none, which will also break the loop here. So I don't expect you to see what the problem is right away, but we can just run it and then look at the output and see what's happening. So here you can see in the beginning it's doing what we expect. We have apple, which is the root node, we push it on the stack. We also have banana, we push it on the stack. And we have dates, we push it onto the stack. Okay, so we pop dates off and then we have banana as the top of the stack now. Okay, but interestingly, it looks like we're pushing dates back onto the stack even though we wanted to keep moving back up the tree. So what's happening here? Notice we visited apple, banana, dates, and it should go back up the tree, so then it would not revisit dates, but it looks like it's revisiting dates and dates again. Okay, so let's see a visual of what's going on. Okay, so what's happening here is, so far it was working when we go from apple to banana to dates, and then it goes back up, so it pops D off the stack, it goes back up to banana, and then from B, what we wanted to do is to check the right subtree, if there's anything, traverse it, otherwise go back up, but we don't want it to go back down to some place it already visited. But what's happening in fact is that when we get to B, the logic is saying, okay, check if there's something on the left subtree. There is, so let's traverse down the left subtree. So what it's doing is it's going back to this node, and we don't want that. So every time we pop D and return to B, we end up pushing D back onto the stack and visiting D again. So we can see how to fix this. Now we're going to see what additional information we need to keep track of for our algorithm to work properly. So again, we're using the stack, but we're also going to track what I'm calling the state. And you'll see what that means in a bit. So again, we start with the root node. We check if it has a left child. It does. We go back down. And so after we pushed A on the stack and then pushed B, we also make a note for node A that we've already gone down to visit its left subtree. Okay, so this will be important in a bit. So now with B, again, we check if it has a left subtree. It does, so we push D on the stack. And we also make a note that for B, we've already visited the left subtree. Okay, now we're at D, check left, check right. Okay, we're all done, nothing there. We can pop D off the stack. Okay, now we're at B. Remember, this is where the original version got stuck. So at B, it's actually had saved information that it already visited the left subtree. And so that way it knows not to do that again. So then it will properly check to visit the right subtree. Okay, in this case, there's nothing there. And then once it's done, we can pop B off the stack. We're at A, and as a similar situation, we already saved the information that we've already visited the left subnode. So we're going to just visit the right instead. So we push C onto the stack. And for A, we save the information that it already visited the right subtree as well. Now with C, we check left, we check right, pop it off the stack. And back at A, now A sees that it already visited the left and right subnodes, and so it can be popped off the stack. Great, so now we visited all the nodes once. Okay, so now let's see how we implement this algorithm correctly in code. We're going to keep track of the state, and I'll do that by defining a class state, which saves the node as well, but it has two additional flags to keep track if we've already visited the left child, or already visited the right child. And these are just getter and setter functions. So here's our preorder with stack function, takes in a tree. So most things are quite similar, except what we push onto the stack is not the node itself, but it's going to be a state object, which contains the node, as well as those two flags. And now what's different as well is we not only want to check if a node has a left child, but we also want to check that we didn't already visit that left child. So if we have a left child and haven't already visited, then we can go down in here. And here what this is saying is that for the parent node, we want to say that we visited the left child, then we want to grab the left child and then visit it, and then we want to create a new state for the child node. So now this node represents the child, the left child, and then we're going to push that state onto the stack. So it's a similar idea with the right child. So now if we run this, we can check that this is doing everything properly. And you can see here, we start out with apple as the root node. Notice left and right have not been visited yet. But then now when we go down and traverse the left child, banana, we can see that apple, the parent, it says that it's already visited the left child, which was banana. And so this is helping us to keep track of whether we've already gone down a certain path. And we can see that the visit order is correct. We go to apple, banana, dates, then cherry. Okay, so now let's take advantage of recursion, which is behind the scenes using a stack. And we'll use that to implement the pre-order traversal of the tree. Okay, so go ahead and implement this function. And remember, in general, when you have recursion, you'll have some function that's initializing some things, and then it starts the recursive process by calling another function. That is the recursive call. Okay, so what I mean is, in general, what you would see with recursion is you have an initializing function, and then it calls something like hint hint traverse, and then within traverse it's calling traverse somehow differently. All right, so go ahead and try this out, and then you can check the solution next. Now let's see how we can define pre-order traversal taking advantage of recursion. We're going to start out defining a list called visit order, and this is what we actually want to return in the end. And we're also going to start traversing the tree from the root. So from the root, then we're going to make a recursive call to a function that we'll have yet to define, traverse, but we're going to start at the root. So let's see what the traverse recursive function looks like. It's going to traverse a node, and it's going to do three things. It's going to visit the node, it's going to traverse left, and it's going to traverse right. Okay, so how do we do that? So to visit, we just say visit order dot append and that node. Okay, let's just get the value of the node. Okay, we're also going to traverse left. So after we visit, we traverse left. We don't want to just pass in node itself because it's just going to cause a loop, but instead we're going to get the left child. Okay, and similarly, after that, we can check the right child, okay, and traverse that. Okay, so there's going to be a few bugs. Let's see what those errors are. If we try to run this, we can see an error that the local variable traverse is referenced before assignment. Okay, so that just means that before we call the function traverse, we need to define it. So let's just call this after we define it. Okay, so now there's going to be another error. Let's take a look at that. We can see that it says none type object has no attribute get value. So what's happening here is that we're probably passing in a none, and then we're trying to get the value and also get the left child, get the right child. Okay, so what we need to check is to make sure that this node object is not none. Okay, so if node is not none, that's what this is saying. If node is something other than none, then we can go ahead and get the value, push it onto the stack, call the get left child, call the get right child. Okay, so how this works too is that notice when you get close to the leaf node, let's say this parent doesn't actually have a left child, so this is actually none. So it's actually calling traverse, passing in none. So it's calling traverse, passing in none, and that's okay because it's going to check. It has to be not none, and then it can continue traversing. But otherwise, it doesn't do anything. It just pops this recursive call off the stack. Okay. So now if we run this, we can see that we get pre-order traversal, apple, banana, dates, and cherry. Okay, now the next two are going to be quite similar to what we already did. We're going to do in-order traversal. So that means traverse the left subtree, then visit the node, and then traverse the right subtree. After you do that, something also very similar is post-order traversal, which means traverse the left subtree, then traverse the right subtree, and then visit the node. Now let's define in-order traversal. It's quite similar to pre-order, so we can actually copy what we already did and then just modify it. So the difference is that we want to first traverse the left, and then we want to visit, and then we want to traverse the right. Okay, so that's in order. So we get dates, banana, apple, cherry. And then similarly for post order, we can take what we already have, which is quite similar, post order. And so now for post order, what it is traverse left, then traverse right, and then visit the node. Okay, so if we run that, we get dates, banana, cherry, apple. Awesome, good job. Now we're going to practice how to implement breadth-first search in code. So as a reminder, breadth-first search is visiting the tree one level at a time. So if this was level 0, we'd visit this node. And if this was level 1, these two nodes, we'd visit all of these first before moving on to the next level and visiting this one. And I just want to mention that breadth-first search is quite useful. You'll see this again when you learn about graph data structures and learn about finding the shortest path. So let's walk through it conceptually. We start visiting the root node, then its left child, and then its right child before we move on to the next level to visit this node here. Notice, unlike DFS, we visited B and C before visiting D. Okay, now let's set up a tree that we can traverse using breadth-first search. So we're going to create a tree that looks like this. The root is apple, and then there's banana, cherry, and dates. So similar to before, we're going to define a node class and a tree class, and then we'll create a tree, and then we'll set the root node's left child to banana, its right child to cherry, and then we'll get banana's left child will be set to dates. Okay. So BFS is actually implemented using a queue. And let's see how this works. We have a queue where we add elements to the queue from here, and then they wait in line, like at a grocery store, and then dequeue, we remove the element that has been waiting in line the longest relative to all the others. So we'll start at the root. We add element A to the queue here. Next, we want to dequeue an element from the queue, and there's only A. So we're dequeue A, and once we dequeue and remove an element from the queue, that's when we say we visited it. So we visited A. And we also want to now add its left and right children to the queue. So we first add B, the left child, to the queue, and then we add C to the queue. Notice that B was added first, so it gets pushed forward, and C was added most recently. So now we're done with A. Now we're going to dequeue the next element from the queue, which is now B, and then we say we visited B. Okay, this is orange. And now with B, we're going to check if it has left and right children and add them to the queue. In this case, B has a child, which is D. So we're enqueuing D onto the queue, and notice C gets pushed forward. And then that's it, we're done with B. So now we're going to dequeue the next item, which is going to be C. So C is dequeued. We say we visited C. See, this is orange. We add any left or right child. In this case, there are none, so we're done with C. Okay, so now we're going to dequeue the next element, which is, in this case, D. When we dequeue it, we're going to check if there's a left or right child to add to the queue. In this case, there isn't, and so we're done. And so now the queue is empty, which means we visited all the nodes. And we visited them one level at a time. A, and then B, and then C, and then D. A, B, C, and D. Okay, so now we're going to write some code. Remember, we want to do breadth-first search, so it's apple, banana, cherry, and dates. And to do that, we want to implement a queue. So to do that, I'm going to actually import dec from collections, which is a double-ended queue. And I'm going to use the append left and the pop functions of it to do enqueue and dequeue. So here's some examples of how this works. But to make it easier to work with, I'm just going to create my own class queue, and it will also use a dec. So when I enqueue, I'm going to use append left, and when I dequeue, I'm going to use pop. And I just also want to double check to make sure the queue isn't empty when I'm popping. And this is to help me when I call print on my queue object, that it will print out what's inside of the queue. So if we run this, we can go ahead and see if we create a queue object, we enqueue apple, then banana, and then cherry, we can see we have apple was inserted first, so it's next in line to be dequeued, and then followed by banana and cherry. Okay, so we add items to the top here, and we remove items at the bottom. Also, if we dequeue, notice we dequeue apple, and now the queue just has banana and cherry. Okay, so now that we have a queue, let's write some code step by step to try to mimic what we did conceptually. First, to keep track of our visiting, let's create a list, and we'll also use a queue. So we're using this queue that I just created, and we're going to start with the root. Okay, we're going to start with the apple, and we're going to enqueue it, add it to the queue. So now we see that the queue has apple. Then we're going to dequeue the next node in the queue, okay, which is apple. Then we're going to visit it. So we visited apple. And then we're going to check if it has a left child, then add it to the queue. If it has a right child, add it to the queue. And as we can see here, we visited apple, and now banana, the left child, is on the queue, followed by cherry. Okay, so now we're going to dequeue from this queue, and next in line is banana. So we're going to visit banana, so dequeue banana, visit it, and then check if it has a left child. If so, add it to the queue. Check if it has a right child. If so, add it to the queue. So as you can see, we did enqueue dates because it's the left child of banana, and we now have visited apple followed by banana. So now we're going to dequeue the next node. Next in line is cherry. So here we get cherry, we visit cherry. If it has left or right children, add it. In this case, it doesn't. And so we can see here, we still have dates in the queue. So we're going to dequeue dates. We're going to visit dates. Check if it has left or right children. In this case, it doesn't. And then we can see here, we now visited apple, banana, then cherry, then dates. And also the queue is empty. So now your task is to write this in code. As you can tell, we repeated a lot of this, so you can imagine you'll be using a for loop. Alright, good luck. Okay, now let's implement the BFS function. So let's write some pseudocode first. So we need a queue. We want to keep track of the visit order. Okay. Then we want to start at the root node. Okay. Add root to queue. And then while queue is not empty, what do? We're going to dequeue the node. We're going to visit that node, add left child if exists, and also add the right child if exists. Okay. And then at the end, we also want to return the visit order. Okay, so let's see how we write this out. Let's create a queue. Let's define visit order as a list. Okay, and let's start at the root. So tree.getRoot, and then we're going to add it to the queue. So we go queue.enqueue. Okay, and then while it's not empty, so while the length of queue is greater than 0, let's dequeue it. So node equals queue.dequeue. We're going to visit it. So visit order.append node. So we visited that node, and then add the left child if it exists. So if node.has left child, then we're going to add it to the queue, and queue node.get left child. Similarly, if node.has right child, we're going to add it to the queue. And then once we're all done with the loop, then we're going to return the visit order. Okay, so let's see if this works. So we want it to be visiting apple, banana, cherry, dates. So we see apple, banana, cherry, dates. Nice. Okay, as an optional bonus task, try to write a print function that will show you all the nodes in the tree and the structure. So here's the root, here is its left and right child, here's the left child of banana, the right child of banana is empty, the left and right children of cherry are empty. And here, node dates has a left child, node is empty, right is empty as well. So the trick here is we're having these empty placeholders so that we can keep track of which node is a child of which parent. So a hint I have is to use a variable to keep track of which level each node is on. Okay, so for instance, the root node is on level 0 and its child nodes are on level 1. So don't worry, this is optional, but might be fun to try out. And yeah, When you're done trying it, then go ahead and check the solution. Okay, now let's see how we can print out the nodes in the tree in a kind of structure. And so I'm just going to walk through the final solution because it might take a while to actually write this out in code. But you can see it's using breadth first search by using a queue. Okay, so what looks familiar is that if it has a left child, then add it to the queue. If it has a right child, add it to the queue. And so what's different now is that I also want to keep track of when there's no child, because I still want to leave a space for it here. As you can see, I want to leave a placeholder even when there is actually no left or right child. So what I'm doing here is I'm going to check if it has a child, then add it. But if not, I'm just going to add none. Okay? And that's going to let me know that when I visit something and there's no child there, then I'm just going to have a placeholder and call it empty. The other thing is that after I've visited all the nodes, I want to be able to print them out so that they're all on their respective levels. This is level 0, level 1, level 2, okay, level 3. And to do that, for my visit order list, I'm also going to keep track of what level the node was on when I append it. Okay? So I'm keeping track of the level, which starts at 0. And for example, let's say the root node is level 0. When I add the children of the level 0 node, they're going to be level 0 plus 1, so level 1. Okay. Similarly, all of these are going to be incrementing the level by 1 when we're adding child nodes. And so this print statement is going to keep track of the levels when it prints things out. So if the level is still the same, then I just keep it on the same row. But when the level of the node is now the next level, then I just want to add a new line character. So when I print it out, it will display on a new line. So as an example, I'm going to create that tree where it's apple, banana, cherry, dates. And I'm going to print out the tree. And you can see there's apple's the root, its left child is banana, right child is cherry, and then banana's left child is dates, and then all these empties are placeholders just to keep everything lined up. Okay? Now we're going to look at binary search trees. And binary search trees are nice because nodes have an order. And because they have an order, when we traverse the tree, we can actually save ourselves a lot of time. Which means when we insert a node, the runtime, the average complexity is log n. Same thing when we search for a node to see if it exists, the average complexity is also log n, where n is the number of nodes in the tree. And same with deletion, log n. So here's how it works. You can see how here's 5, node 5, and then 6 is greater than 5, so it's to the right of node 5. 4 is less than 5, so it's to the left of 5. 2 is less than 4, so it's also to the left of 4. And notice that everything in this left subtree of 5 is less than 5. Everything that's going to be in the right subtree of 5 is greater than 5. Okay, now let's set up this notebook so that we can implement some functions. First, we're going to define a node class, which we've seen before. And also, just for the sake of a print function for the tree, we're also going to use a queue so that we can traverse it breadth first search. All right, now let's continue on with the lesson. Now we're going to look at binary search tree insertion. So here, let's say we have a tree. We want to insert 5. Right now the tree is empty, so we'll just put 5 as the root. Next, we want to insert 6. So we notice what we do is we check and compare 6 to 5, and 6 is greater than 5, which means we'll insert to the right. Since there's nothing else on the right, we'll just go ahead and let 6 be the right child of 5. Next, let's insert 4. So we start at the root again. We compare 4 to 5, and 4 is less than 5, so we insert to the left. Since there's nothing here so far, 4 can be the left child of 5. And now let's insert 2. Again, we start at the root, we compare 2 to 5, and 2 is less than 5, so we're going to traverse to the left. Since there's already a left child here, we'll do another comparison, and 2 is less than 4, which means we'll insert it to the left. Okay, so there's a question of how you handle duplicates, and this can be a design choice. So what happens if you already have 5 in the tree and you insert 5 again? Well, one option is to just override that value, override the node. Another option would be to keep a count of how many times you've inserted that node. So if you've inserted 5 a second time, that counter gets incremented to 2. And another option is to keep a list of the duplicate nodes. This might be helpful if the node value is a key, but each node may actually contain additional information, and so they're actually slightly different, and you want to just keep track of all of them in a list. For our exercise, we're just going to assume option 1, that when there's a duplicate, we'll just override it. Now we're going to define insertion in code. And so one way to do this is with a loop, and another way to do insertion is with recursion. So you can try one or the other, or both, and when you're done, you can see if it works by inserting a couple nodes and checking what it looks like. So once you've tried this out, go ahead and check out the solution. Okay, now let's walk through the solution of insertion. First, I defined a comparison function just to be more general, because when you're comparing the values, if they're simple things like numbers, you can say one is less than the other. If the value is some kind of object, then you would want to figure out what in the object you want to compare with the other. And so I'm just writing this to make it more general. But here we're just going to return 0 when the values are equal, -1 when the new value is less than the current one that's being compared to. In other words, when we want to traverse left, return a -1. And then we'll return a 1 if the new node's value is greater than the current node that is being compared to. In other words, we return 1 when we want to traverse to the right. So here's how we can insert using a while loop. We have the new value. We're going to wrap it inside a node object. We're also going to get the root. And if the root is actually empty, that means we have an empty tree. We can go ahead and set the root to that new node. Otherwise, we're going to use a loop to walk down the tree. First, we'll do a comparison of the new node and the current node. In this case, we're starting out with the root. And if they're equal, then we'll just set the value of the node to the new node's value. And notice that because this node may have other children nodes already, then this will have a left and right pointer. And so we don't want to say node equals new node, because the new node is something we just created and it doesn't have pointers to the left and right children that this current node might actually have. Alright, so that means we've inserted the node, and so we can go ahead and break out of the loop. So stop looping. Otherwise, if the comparison is -1, I define this to mean we want to traverse to the left because the new value is less than the current node that we're comparing to. And if the node already has a left child, then we want to continue traversing left. So get left child becomes the new node. And then at this point, we're going to be returning back to the top of the loop in this case. Otherwise, if there is room to set the left child to the new node, then we'll go ahead and do that. And that means we've inserted a node so we can break out of the loop. So we'll stop looping. Okay. So this is the case when we need to continue traversing down the tree, so we continue on with the while loop. And this is the case when we've found a place to insert the node, and so we can stop traversing and break out of the loop. Okay. And it's the same thing when we go down to the right subtree. Now with recursion, we can do the same thing. So here we'll start out checking if the root is none. If so, we can just set the root to that value, and then we're done. Otherwise, we're going to make a recursive call to this helper function right here. We're going to pass in the root and also the node containing the value that we're trying to insert. So now what this is doing is it has a current node that it's comparing to and also the new node. So we'll do a comparison, and then if they're equal, then we should set the value to the value of the new node. We're overriding it essentially. Otherwise, if it's -1, it means we need to traverse left. Okay? And this is similar to what you saw before. If the node already has a left child, then we're going to continue traversing left. And here we can use a recursive call to this function, so we're calling it again. And now we're passing in the node's left child as well as the new node that we're trying to insert. Otherwise, if there's room, we can set the left child to the new node, and then we're done. Okay? And similar with the case when we need to traverse right, when the value of the new node is greater than the current node, then we're traversing right. Okay, so now let's try this out. We're going to insert a couple values here. We're also going to insert a duplicate, which should be overridden. And you can see here's a tree. 5 is at the root. 5's left child is 4, and its right child is 6, because 4 is less than 5, 6 is greater than 5. And now 4's left child is 2, because 2 is less than 4, 2 is also less than 5. Similarly, with the recursive version of it, we should get the same results. Now we're going to look at searching inside a binary search tree. And it's quite similar to what we did with insertion. So we have a tree here, and we want to check if 4 exists in this tree. So we'll start out by comparing it with the root. Here 4 is less than 6, so we're going to traverse to the left. Now we compare it with 3. 4 is greater than 3, so we go right. And now 4 is not in this subtree of the right subtree of 3. And if it did exist in there, it would be in this right subtree. But since 3 doesn't have a right child, we know that 4 is not there. So we can return none, or we can return false, depending on the implementation choice. Here's a second example. We're going to search for 7 to see if 7's in the tree. We'll start at the root. 7 is greater than 6, so we'll traverse right. Now 7 equals 7, so we can return this node itself, or true. And the reason you may want to return this node is it might store some additional information that's not in this node that you searched for. And so you can return the node to extract some saved information in there. Okay, now let's define a search function. And it will return true if the node contains that value. Otherwise, it will return false. So go ahead and implement search right here. Now let's take a look at the solution for a search. We're searching for this value, and we'll start at the root. So the current node is going to be the root. And we'll also wrap the value inside a node object, so we'll call this the search node. And we'll use a loop to traverse the tree. We'll do a comparison of the node and the new value. If they're equal, then we found it, return true. Otherwise, if the new value is less than the current node, then if the node has a left child, then we'll traverse left. Right? And then we'll continue on with traversing down the tree using the loop. Otherwise, if there's no left child, then we know that the node isn't there, the value that we're looking for isn't there, so we'll return false. Similarly, when the value is greater than the current node's value, then we'll traverse right. If there's a right child, then we'll continue traversing right. And then here this node goes back up to another while loop. Otherwise, if it's none, then we return false because we know that the node isn't there. The value we're looking for isn't there. Okay, so let's try this out. If we create a tree, we insert a couple things, and then we search for 8 and search for 2. Let's see what happens. So 8 is not there in the tree. We did not have 8 in the tree. So it's false. 2 is in the tree, so we find it and we return true. Now let's look at deleting a node from a binary search tree. So there's 3 cases we'll look at. One is when the node we want to delete is a leaf node. Another case is when the node we want to delete has 1 child node. And another case is when the node has 2 child nodes. So here's the first case, when it's a leaf node that we want to delete. Let's say we want to delete 4. So we traverse down until we find 4, and then we set the pointer of its parent. So this parent is 3. We set its left child pointer to none to remove 4 from the tree. Case 2 is if the node has 1 child node. So let's say we want to delete node 3, and it has 1 child node. What we can do is, for this node's parent, which is 5, we want to set its left pointer to point to its child. So it's going around 3, and we can also set node 3 to none to delete it. Here's a third case, if the node has 2 child nodes. So let's say in this tree, we want to delete node 7. It has a left child and also a right child. So we want to find the next highest value in order. For example, there's 3 and 4, 5, 6, 7, 8. So the next highest value from 7 is 8. Okay? And we find this by going to the right subtree of 7, the one we want to delete, and then traversing all the way to the left to find the smallest value in its right subtree. Because remember, everything in the right subtree should be greater than 7. Everything in the left subtree should be less than 7. But then if we go here, then within this subtree, to find the smallest value, we just keep traversing left until there's no left child to traverse, and then that's the minimum value within this right subtree. What we'll do is we copy this value, and then we replace the value in this node with this copied value of 8. Then for this node that we just copied over, we also want to remove it. So we have its parent, which is 9, have it point to its left child pointer to the right child of 8. And we'll also set node 8 to none and delete it.
In my conversations with Udacity students over the years, something I've heard again and again is that people switching career tracks or even just acquainting themselves with new fields can experience issues with self-confidence. They often doubt that they've developed solid expertise, feel like they don't belong in their new line of work, and attribute success they experience to luck rather than their own effort and progress. It's like their sense of identity hasn't yet caught up with the growth they've undergone. This is called imposter syndrome. The good news is that it's super normal to feel this way, and it's something you can work through if you experience it.
So true. I taught a coding bootcamp before, and nearly every one of my students admitted to me at some point that they couldn't imagine doing data science for a living or getting a job in the field that they really wanted. One of my students made beautiful map visualizations and still insisted that he couldn't imagine himself getting a job. Another one of my students wrote efficient, well-documented code, but she still told me that she felt like she had to work a lot harder to prove herself because she didn't have the right background or the right credentials from the right university.
And how about you, Eddie? You've done a ton of online learning and you've switched fields yourself. Have you ever felt something like this before?
Yeah, definitely. I felt it too. When I enrolled in my first Udacity nanodegree program, friends would ask me, "What's new with you?" or "What are you up to these days?" I would get pretty self-conscious and mumble something like, "Oh, well, I'm studying something online, some data stuff." And then I would stare at the floor before changing the subject to, "Enough about me, how about you?"
Oh my gosh. Yeah, imposter syndrome is a really, really tricky problem to handle. If someone tells you just believe in yourself, that may not necessarily help because the question is how. How do you shake the voices inside your head and build up your own confidence?
For me, what helped me handle the self-doubt was to put that question aside and instead ask myself some different questions. If I somehow knew that in the future I was going to be in my ideal job doing cool things for work, what would I be doing these next 6 months, 1 year, and 2 years to get there? As a follow-up question, I would ask myself, what would I be doing today?
Yeah, that sounds helpful in getting yourself comfortable with trying new things and going after your goals, even if they seem kind of out of reach right now. I've also battled some really intense imposter syndrome as a woman in physics, a self-taught programmer, and an educator with a non-traditional background.
Oh wow, how did you find ways to deal with that?
I mean, I still struggle with it sometimes daily, but I found some strategies useful in trying to combat it. For example, if I'm feeling like a fraud in my work, I'll try to imagine how I might respond if someone else, other than me, with the same skill set was doubting themselves in the way that I do.
Yeah, I can imagine we're usually harder on ourselves and more forgiving of others.
Definitely.
So it helps to think of how we treat someone else who was in our same position.
Totally. And similar to what you were saying, I've worked really, really hard to become more comfortable with risk-taking, receiving feedback, and just putting myself out there. Pushing myself outside my comfort zone this way felt totally terrifying at first. I made it more palatable by reminding myself of a few things. Number one, my belief that I can't succeed is not objective reality. It's just a thought that I can make fade over time. Number two, my brain and everyone else's brains are capable of unbounded growth, and feeling challenge often indicates that I'm making progress. And number three, my career development and the impact I want to have through my work are way more important than a bit of discomfort on my end. So reconnecting with my own goals puts all of this in context.